Okay, view full screen. Good morning. This is chapter 7 and 8 on really the atomic theory in a generic way. It is going to be presented, as I mentioned earlier, as the history of the development of atomic models. Starting with the Thomson raisin pudding model, we will evolve to the Bohr models and the Rutherford model and the Schrodinger model and add appropriate calculations. They're not very difficult, but they are classic in their nature. Okay? So when we talk about the study of the atom, the first thing is rather obvious to all of us. We can't visually see an atom. So why do we believe in their existence? Well, we've been indoctrinated over the years with the fundamental, that's made up a bunch of atoms. Okay, fine. So we believe in atoms from an existence standpoint. Okay? But the proof of the presence of atoms and elements and so forth and so on comes from what we call the indirect evidence of what the atom is saying to us. And that goes back to system and surroundings. So it's based upon empirical evidence. Now, what does empirical evidence mean? It is the relationship between one dimension and another. How do we relate what we see in that glowing atomic tube, is what we, discharge tube, to the atom? Well, it sends out light. Well, what do we know about light? Well, light, if you look through a prism, you've all seen this. You've seen the continuous spectrum, that thing up there, which is refracted and through the prism. And everybody sees a rainbow, Roy G. Biv. Okay? But when you look through a prism at a discharge tube like this, you see a bright line spectrum. See these little lines like this. And I can get my book. Every atom has its own fingerprint, referred to as a bright line spectrum. So if you can kind of see this, this comes out of the 10th edition, 269, if you happen to have that text. Just in the 9th edition too, so if you want to look it up. But say hydrogen has 4 lines, if you can see them from cheap seats back there. Helium has 1, 2, 3, 4, 5, 6 lines, okay? And every element on the periodic chart has its own specific set of bright line spectrum. And they are waves of light. And so in the empirical evidence, we study the atom in terms of the wavelengths of light. So you might make a brief note, study atom terms of wavelengths of light. Okay, right there. A couple of ways to deal with this is to make the atom an excited atom. Okay, what does that mean? If I were to draw, say, a hydrogen, it would have a nucleus and 1 electron, okay? Very simply put, nucleus and 1 electron. You have to believe that there are other levels. As a matter of fact, this atom right here actually has Let me see if I can draw this where it looks fairly decent. Here's the first level, second, third, fourth, fifth, sixth, and seventh. We've done this little diagram before. Well, when the electron is in the first level, N equal 1 for hydrogen, that's the lowest energy state. That's called the ground state. Helium has 2 electrons. When those 2 electrons are in the first ring, it's in the ground state. If we go to lithium, it'll have 2 electrons in the first ring and 1 in the second ring. And while they're there, that's called the ground state. It's the lowest energy existence of the various elements is when the electrons are in their ground state. However, if I add energy, electric shock, for example, in this one, electric current, however you wish to define it, we can see it affects the elements. You can't see anything here. You just have a glass tube, okay? But when I run a charge through it, I get this lavender color. So what I'm doing is I'm causing the electrons, which are around the nucleus, to absorb energy and move away from it. And in doing so, I'm not going to leave that on, but until we get ready for it. In doing so, it can do one of 2 things. The electron can go out to the first level, or that electron can go out to the second level. I know that sounds like 3 levels. It could stay in the atom, number 1. That's really what I'm saying. The electron can stay within the electronic structure and the rings and so forth. Or it can go completely out of the electron configuration of the atom, right? And that's called ionization. That's when the electron leaves atom. Let's see if you can't read that. It says electron leaves atom. We're interested in the behavior of the electrons that do not leave the atom. Now, as the electric charge is directed through the atom, these electrons will absorb energy. And I'm going to take one out here. Let me change colors on this so you'll have a better appreciation for it, I hope. Okay, let's say we got electron, blue electron out here, and then we have the same electron. These are the same electron, and then we got one here, the blue ones. Okay, the reason they got out to those positions is they absorbed energy. It's like me throwing a pin in the air. Okay, it didn't leave the building, but it went to a certain height, and at the top of its path, it has the most energy. We didn't see that. It's called energy absorption. There are absorption spectra, but we're not interested in that right now. It has absorbed energy. Now, if it goes up to that level and comes back down to the same level, it gives up whatever energy it absorbed. Absorb, give it up. When it gives up that energy, it can be seen if it ends on the n equal 2. That n equal 2 level is the visible spectrum level. The electron has the option to actually go back to the first level in every case if it wants to. But you can't see that because it's in what we call the UV range. And I'll show you, we'll discuss that again in a minute. But if it ends on the second level, this second energy level, let's see if I can find something that looks like a second energy level you can remember. There it is. I think this can be seen right here. It gives off light, that visible light. So ending electrons falling to the second level. yield visible light. In the form of bright line spectrum. So, if the electron goes out to, let me number them. This is 3, 4, 5, and 6. So, if the electron goes from 6 down to 2, say, right there, we'll get rid of this one for the short term. So, I'm going to go N equals a 6 to 2 transition. That's what we call it. Electron transition. What it will do is give off some 1, 2, 3. Let me see them. 1, 2, 3, 4. It gives off a violet band of light. If we go from 5, say this number 5 right here, goes to 2, right there. So N equals 5 to 2. It gives a blue band of light. Okay, so we got a blue band of light. We got a purple band of light right here. If it goes from 4 to 2, it gives off a green band. And if it goes from 3, and then use blue there, there we go. It goes from 3 to 2, it'll give off a red band. The bright line spectra of the hydrogen atom, when looked at through a spectroscope or a diffraction grating, if I can find it. I got a blue down the violet. You will see for the 3 to 2, you will see a red band. Just like that. When you look through, it's kind of like looking through a prism at white light. You get this right here, the continuous spectrum. Let me finish this and I'll give you a spectroscope. If the electron is moving from 4 to 2, it's going to give off a green line band. Very sharp line. If it moves from 5 to 2, it's going to give a blue line way down here. And then finally, it gives a purple line. These are fairly close together right there. And that represents what we call the bright line spectra of the hydrogen atom. Now, so what? We got a bunch of lines on a piece of paper. Well, the idea here is to take this data and translate it into a picture of the atom. And we're going to do that as we go along. Now what I'm going to give you right now, and then we'll pick it back up when we get into that part, are the wavelengths. And I'll say the following, okay? The red line, what we call lambda, lambda is a little squiggle that looks like that Greek letter, 656 nanometers. It's not 657. It's not 650 5, it's 656. And so it's a discrete wavelength. Means it's only one wavelength, not multiple. If it was multiple, you'd see the bright line spectrum. The full continuous spectrum, not the bright line, the full continuous spectrum. The green's 486. The blue line is 410. Actually, 410.1 according to some of them. Let's see, this is the green, and this is the blue. This is the red line, and it was 433. 434, good enough. And the violet line is 400, wait a minute. Yeah, 410, yeah. 410 nanometers. Now they do have one out here, another line that you can't see because it did, if you go back to the atom, there is a 6-to-2 transition. But because of the amount of energy and the distance of the fall, it's a lot of energy. It goes into the UV range. You can't see it out there. But it has been determined to be about 397 nanometers. So we see the wavelengths are very discrete. The word discrete is very important in here in that there is no spread of wavelengths. There's no band of wavelengths. It's a given specific number that's associated with those red lines. That means it's in number 3 or it's in number 2, but it never exists between the two. Or it's in number 4 or the electron is in number 2, but not in between. It transitions from whatever level it starts in to the 2 level or 1 level or wherever it decides to stop. That's called a quantum leap. It's a very, very discrete amount of energy for each one of these bands. And that says, okay, here's the nucleus. That electron's orbiting that nucleus. That was from the Rutherford theory. And it's going to transition from there down to wherever it's going to go. So it's got to be living in a ring, like planets orbiting the sun. That was the Bohr model. In due time, wavelengths of light and light will lead to the modern quantum model, which we will look at in detail when we get there. But this is what the study of the atom is all about. Stimulating the atom or quantity of sample that is, in that case, only hydrogen, stimulating it and determining what that atom is saying to us while it is undergoing these transitions. The atom, of course, is the system. And the spectroscope, your eyeball, are the surroundings. So in the study of the atom, is what I'm trying, all this is involved. The atom equals a system, and that atom is sending light signals, wavelengths, to surroundings. That's you. Or the spectroscope or whatever instrument was invented to detect the signals. And you've heard me preach this over and over and over again. You are not measuring anything in the atom. You're measuring what the atom is sending to you. And in this case, the language is wavelengths of light. Okay. So that is, in essence, the wall or ideas that the scientists have to penetrate. They have to penetrate the atom in something they haven't seen, or something like a collection of items in a shoebox that you've taped together, that you have to find out and decide on what the content of that shoebox is. So in order to do that, what would you do? Probably the first thing you would do is shake the box and hear it rattle. Well, what is that system saying to you? It's some noise of whatever's in the box. It's sending signals to you. And the effort is translated, and whatever you see is translated into, well, I think it's a wrench or screwdriver or a set of screws or whatever. And that's what has been done in the study of the atom. It's empirical data translated into the picture of the atom. Now, in your outline, there is a few comments on the history of development of particles of the atom. If you have your outline or not, just remember, it serves no purpose for me to read all this to you. J.J. Thomson was the first one to discover the electron. Okay, that's fine. Okay, but then Millikan discovered the charge electron mass ratio. That all went into the big picture. The proton was co-discovered by Goldstein, Becquerel, and Rutherford. And the neutron is James Chadwick. H.G.J. Moseley was said to have identified the proton also, but he was killed in World War I and never got a chance to publish. Here you will need these, but we will develop them as we go along. These are postulates that associate with the various atoms. Now these again are already printed in your outline. The top one up here is the Rutherford model, and it goes down to right here. You can see the Rutherford model, and we're going to develop these in just as we go along here. And here's the Bohr model, the postulates that they came up with from the language that the light is sending to us. And down here is the Schrodinger model and what the atom evolved to be in their minds. And they published it, and this is the Schrodinger model that is the current understanding of what the atom looks like. And we use that in developing chemical reactions, how one element connects to the other and then builds molecules, interacts through other reactions, is all defined in terms of the Schrodinger model. You may remember 1s2, 2s2, 2p6, 3s2, 3p6, those things in previous courses. Those are the Schrodinger model designs. And they're based on quantum numbers associated with the electron's behavior in the atom. But this is very important, and again, we will develop those as we go along. There's a reference sheet right here which defines the quantum numbers, and we're going to use what is called the Aufbau diagram to write electron configurations. You may have seen this or remember this from earlier courses right here, but it defines the building up order of the electron structure of the atom, and starting with the lowest energy going to the highest energies. And we can build a schematic picture of what the atom's atomic structure is. We'll get there. May not be today, but we will get to most of it. Okay, that's the history of the modern atomic theory. I want to drop down to the basic atomic structures, part 2 in this outline, substructure, structure, atom, variation, all that we've already talked about in the earlier parts of the course. There are 2 variations in the atom. Electronic, which is gain or loss of electron by oxidation reduction. You got bound to remember a little bit of that. And isotopes. Every element has the same atomic number, but a set of elements that have different atomic masses. Those are isotopes. So you have nuclear variations and electronic variations. We're going to focus on the electronic variations. And I think we can leave the nuclear variations until deep second semester somewhere. Okay. We call this atomic dimensions. The first model of the atom was the Thomson model, and it didn't survive very long. But the second one was the Rutherford model, and basic atomic dimensions were defined by the Rutherford team. And so you can simply say this is from Rutherford's shell model. In general, we can say the shell model has average dimensions. And what does that mean? Average dimensions. That means an average diameter, an average mass or weight, and an average volume that are considered, on the average, relevant. If you wanted to talk about the dimensions of the atom, you talk about it in terms of average linear dimensions and so forth. And I'll show you. Okay, we will begin now with the average diameter of the atom. And it says in the little problem, is classic. This is not designed to be a brain teaser or anything. Everything's there. Given the diameter of a nucleus of an atom, that's to be 1 centimeter. Approximate size of a marble, small. You can make anything. Sometimes we do it in the size of a BB, 1 millimeter or something. You make up the size of the nucleus. What is the radius of the atom relative to this nuclear diameter that you've chosen? Okay? How do you define that? Well, the average atomic diameter is about 10 to the minus 8th of a centimeter, and the average radius, diameter of a nucleus is 10 to the minus 13 centimeter. So, how many nuclei divide into the diameter of the atom? So we draw a picture. So I'm not very good at pictures. But the nucleus, of course, is in here. Right here. And so the average diameter is 10 to the minus 8th of a centimeter. Now, I'm just going to point this out. The average diameter of the nucleus, Nu, is equal to 10 to the minus 13 centimeter. Okay, very little. Now, the number of nuclei per average diameter equals the average atomic diameter divided by the average nuclear diameter. So if we divide 10 to the minus 13 into 10 to the minus 8, we get 10 to the 5th nuclei per atomic diameter. That is, in a general sense, if nucleus equals 1 centimeter diameter, then the atomic diameter is equal to 10 to the 5th centimeters. So 1 nuclear diameter, and if I want the atomic diameter, I have to have 100,000 of them lined up all the way across. So what you need to remember is one atomic diameter equals 500,000 nuclear diameters. That's simple. So for our problem, we're given nuclear diameter to equal 1 centimeter. Therefore, atomic diameter is equal to 500,000 centimeters, or 5 times 10 to the 5th centimeters. That's kind of tough to visualize, okay? Let's put it in terms of a radius. I mean, you can, at this point, you can manipulate the picture that we've drawn up at the, there we go. So an average radius is half of that number, which gives us 2.5 times 10 to the 5th centimeters. Let's convert that to yards, and you can compare it to football fields. How many football fields does it take from the nucleus, where I'm holding the nucleus, where's the electron? How far away is it? So we're going to go to yards. Very simple dimensional analysis. So how many yards equal 2.5 times 10 to the 5th centimeters? And so we want to go get rid of centimeters. We go to inches times inches and yards. So it's 2.54 centimeters in 1 inch, and 1 inch, 36 inches, excuse me. 1 yard is 36 inches. The centimeters drop out, inches drop out, and we have it in terms of yards, to generate some visual perspective of what the atom looks like. So this is 2.5 times 10 to the 5th divided by 2.54, divided again by 36, and that's in yards. 2,734 yards. Okay? How many yards in a football field? 100. So we'll move over 2 places. So that's roughly 27 football fields. Or you can go on to miles, something like that, and I'll let you do that one. But it comes out about 0.6 mile from nucleus. So if we had a nucleus and an electron, the distance between the nucleus and the electron is about 0.60 miles, like that. Now, the only thing you need to remember is the top bracket up there. 1 atomic diameter is 500,000 nuclear diameters. Choose whatever nuclear size you want, baseball or basketball or BB, and multiply it by 500,000 and convert it to something that's dimensionally understandable. Football fields, 27 football fields. That's quite a ways, or points half a mile roughly. It's an average, so it is established as that. So learning element number 1 is what's the dimension, linear dimensions of the atom. Or nuclear masses versus atomic masses. It says in the problem here, the absolute atomic mass of helium. Now we're talking about it containing 2 protons, 2 neutrons, and 2 electrons. And if you look at the back of the Ebbing text, you can get what we call the rest mass values of the protons, the neutrons, and the electrons. And so 2 times the proton mass, rest mass, 2 times the neutron rest mass, plus 2 times the electron rest mass, 9.11 times 10 to the minus 31 or something like that. Add those together and you'll get 6.6978 times 10 to the minus 24 grams. Okay? Calculate the weight percent represented by the nucleus. That's nuclear weight. Here's the nuclear weight right here. And the electron cloud weighing 1.8 times 10 to the minus 7 grams. So it is nuclear over total mass times 100. Electron total mass over atomic mass times 100. And we'll compare the two in terms of mass. What mass contribution does the nucleus make to the atom, and what mass contribution does the electron make to the atom? So if we say weight percent is equal to mass of item divided by total mass times 100%. Okay? So the weight percent contribution of nucleus is the weight of the nucleus divided by the weight of the atom times 100. Okay, so we're talking about weight percent nucleus is equal to 6.696 times 10 to the minus 24 gram divided by 6.6978 times 10 to the minus 24th of a gram times 100%. Okay, so that ratio comes out 99.973 weight percent of atomic mass. Well, the weight percent contribution of the electron cloud, let's just generalize all the whatever the electrons are doing, weight percent electron is equal to 100 minus 99.973 percent by weight, and .027, yeah, weight percent of atomic mass. Now the generalization here is straightforward in that all you can say really, you know, based on this, is the mass of the atom is 99.9% nucleus. The rest of it is electron. You don't have to remember the specifics, but I'm not going to ask you those numbers. You can look those numbers up anywhere. What I'll ask you is, for an average atomic mass, how does the nucleus compare to the mass of the electron cloud? And then I had probably qualitative quotes down there. The nucleus represents on 99.9%, or the nucleus represents 99.973% of the total mass of the atom. So when you look at the periodic table and you want to talk about atomic masses, the atomic mass on the periodic table is considered to be only neutrons and protons, okay, in terms of mass, because of this classic derivation right here. So that was mass relationships. Linear relationships are what? 1 to 500,000. You make up whatever nuclear diameter you want and then translate it into the dimensions you want. Nuclear mass, 99.9% is nucleus, and the rest of it is electron. That's about best you can say. Now you can memorize the numbers if you want, that's fine. Hope I got all that on there. Well, maybe I can do a little better. So now we want to take the problem 3 and look at how many nuclei can be stuffed, so to speak, in one atomic volume. Okay, how many atomic nuclei would be required to fill a spherical volume of 5.233 times 10 to the minus 25? So we got given atomic volume equals 5.233 times 10 to the minus 25 cubic centimeters. Okay. And we have to calculate the nucleus. One of these days I'm going to change that. Nuclear volume is equal to 4/3 pi r cubed. And the, of course, r of the average, the radius average atom is 1/2 of 1 times 10 to the minus 13 of a centimeter. So that's half of 0.5, 5 times 10 to the minus 14th of a centimeter. So really the question is asking you how many 5 times 10 to the minus 14s go into 5.233 times 10 to the minus 25. Actually, it's 5.233 times 10 to the minus 14. I don't remember. That's the way this thing will work out. And so I want to cancel out that coefficient number. So why don't you change that to 5.233 times 10 to the minus 14 cubic centimeters. That's the radius. I was looking for something. Okay, so that's the radius of the nucleus. And so take some of that back. Okay, so the volume of one nucleus is 4/3 pi r cubed, and that's 4/3. I'm going to use just 3.14, and then 5 point. Let's just use the 5 times 10 to the minus 14. Come to think about it, that's not cubed right there. That's something else. Centimeters cubed. All right, now we've got the right number. Sorry. You need to leave that off part too. My bad. Okay. So let's do the 3.14 times 5 times 10 to the minus 14, and that's equal to that times 4 equals divided by 3 equals, okay, 2.09 times 10 to the minus 13 cubic centimeters. Let me double check that. Should have come out the same in here with that radius. Okay, let me back this up here. 5 times 10 to the minus 14th centimeter. It's 5.233 times 10 to the minus 40 centimeters cubed. That's the nuclear volume. There we go. Now, the number of nuclei in one atomic volume is what we're calculating. Number nuclei equals, we've got 5 times 10 to the minus 14 centimeters cubed. No. Come on, JP. Here. 5.233 times 10 to the minus 25 cubic centimeters. I'll get warmed up here in a minute. Okay, and then 5.233 times 10 to the minus 40 cubic centimeters. And that drops off. So we really have 40 minus 25. Let's see, 40 minus 25. So that is 1 times 10 to the 15th nuclei per atomic volume. Now what that translates to, guys, is 1 comma 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 nuclei per atomic volume. That's 1,000 times a million million. There's your millions. So we went 1,000 times 10 to the 6 times 10 to the 6 nuclei per atomic volume. Okay, so you need to kind of remember that one right there, or 10 to the 15th up here. So that's 3 issues. Linear, 1 atomic diameter equals 5 times 10 to the 5th nuclear diameters. Mass is 99.973 weight percent equals the nuclear mass, and 0. whatever it was, 027 weight percent equals electronic mass. Put that up there as that. And the third one was the volume relationships, which is 1 times 10 to the 15th nuclei equals 1 atomic volume. Now those are not hard relationships to keep in mind. And the types of problems will be generic in that, okay, assume a 1 millimeter nucleus, what's the diameter of the atom? And you have to remember 500,000 millimeters and then translate and you'll have your answer choices like that. And so the purpose here is, of course, this is part of the chapter we're studying, but it also contributes to your future knowledge of being able to at least discuss this in a general terms based on the Rutherford data. Now, what does this all say? The most important conclusion out of all of this is this: the atom is mostly space. Based on the numbers, I think you would somewhat agree with me on that issue. I saw a video not too long ago where somebody said the entire universe could be compressed down to the size of a softball. If you take out all the space and particle mass and volumes and so forth. And they use that a lot for the source or a theoretical reference point for the existence of the Big Bang. And so they trace it all back to, well, if everything was squished down, you could actually get to a black hole the size of a, okay, well, that's fine. Okay, but your responsibility is just the generic stuff. I don't expect you to define cosmic evolution, but at any rate, this is, okay, theories of atomic models. As I've mentioned a couple of times before, there are 4 historical models of the atom. The Thomson model, let me do it in a different context here. Raisin pudding. Raisin I-N or E-N?
I am.
I am, thank you. Rutherford shell model. The Bohr concentric ring model, and the Schrodinger, S-C-H-R-O-D-I-N-G-E-R, Ernst Schrodinger. I've got 2 dots in German origin. Quantum model. Some people call it the modern quantum model, as the current perspective on what the atom looks like. Okay, let's start with the Thomson model because it goes very quickly, and then we'll move into the Rutherford. It'll take a little longer. Then the Bohr model will take longer than that, and then Schrodinger model we'll use through the, well, actually the Bohr model and the Schrodinger model through the rest of the book. So perspective on where you're going is in terms of how long I take to go through these. Okay, the first one is Thomson model. Is based upon opposites attract theory. At the time this concept evolved, scientists were well aware of the electrons and the existence of positive nuclear particles using what they call cathode ray tubes. Cathode ray tube, I'm not getting down again. Cathode ray tube is a glass device. And it's got a little valve out here for vacuum. And on one end it has a electrode that's sharp on one end. Then you have a collector on the other end, and this thing is connected to a battery or a transformer. The short side is symbology of negative, long side symbology is positive. So this would be a negative electrode here, and on this end be a positive electrode. When connected, what you see is a green beam going between the negative electrode and the positive electrode. If a magnet were brought close to it and a negative magnet, what you would see is a deflection going away from it. So let's say we're talking about a magnet. That says magnet, believe it or not. What we'd see is a repulsion effect like that. If you take the positive end of a magnet and push it up against the green beam, let's see, it would repel from that. I should put the magnet on the other side. Let's see, the plus end, it would go toward the plus end, and the orange would go toward the negative end. I think everybody can appreciate that. Opposites attract, like charges repel. Okay, so he drew the conclusion that the atom is a spherical entity has no specific organization inside the sphere. And he made the postulate that the overall atom was positively charged, or the vapor, or whatever he called it. So the overall surface charge, or throughout the atom, was in general positively charged, and electrons were distributed evenly as raisins suspended in a gelatin-type pudding. There was no definitions of, well, I'm kind of losing my greens, but you get the idea. The electrons were suspended like a gelatin, like raisins in a gelatin pudding. Well, as science moved on, that was discarded, and Rutherford did the following work in his laboratory, in his group, and this defines the origins and history of the Rutherford shell model. The Rutherford shell model has kind of two issues that you need to be aware of. One is the experimental foundation for the Rutherford model, and two, the postulates of the Rutherford model. And we use the Rutherford model when we work the three problems. So those conclusions about the dimensions of the atom, those three, the linear, volume, and mass issues, are from the Rutherford measurements and experiments. But the first thing we need to look at is the gold foil experiment. Now, in this experiment, he had a lead block, and I'm drawing a crude representation, certainly, that he drilled a hole in, and he put an alpha generator, a heavy element that had alpha radiation generated. And at the point in time, they knew about radiations, and certain elements like uranium gave off high quantities of alpha particles, which were nothing more than helium nuclei. So what we're going to do is shoot these alpha particles, alpha particle source, and these little particles, at a gold foil that is suspended in a chamber lined with photosensitive coating. And better than that. So it had a photosensitive coating inside, around like that. And he shot the alpha particles at a strip of gold foil. What were his observations from that? Well, he observed most of the particles went straight through, and the back of the photosensitive, or the furthest point straight through the gold foil, was mostly exposed. The highest number of particles went right in through without touching anything. It's like throwing a bunch of tennis balls at that wall and they go through it. And that was certainly unexpected. And I don't think using that as an analogy. A small amount were observed to deflect off at obtuse angles. Okay, and with their equipment and measurements, they came up with the relative charges and masses and dimensions and stuff that we looked at. And one that he came up with that was very, very small, where some of the particles were reflected or deflected straight back at the source, bounced straight back. Now, keeping in mind that the alpha particle is a helium nucleus carrying a +2 charge, just as a reference right there. The conclusions that he drew from the experiment: one, the atom is mostly space, which we've already talked about. So these are Rutherford postulates. These are also written down for you for your review if you want to. And they're in your outline, second page over or so, and you can follow me through these. It's mostly space, but the electrons occupy all of that space. Now, he did not define the concentric ring or the orbital behavior and stuff like that. He just said it's just a cloud. That's all he said. So the second one is electrons occupy most of atomic space. Now, the most radical conclusion of the Rutherford model is that the atom is two parts: a dense positive nucleus and a diffuse electron cloud. So you can see it. Y'all got the top part up there? He goes on to say something in the general sense. It says a near miss of a nucleus by an alpha particle results in repulsion, deflection. Well, an alpha particle is a positive close to nucleus, which he saw as positive, results in deflection. Therefore, nucleus has a positive charge. Okay? He was the first to propose a two-part atom, nucleus and electronic cloud. So that's a generalization you need to keep in mind. Okay? First to propose two-part atom. Very important little note there. I think it's easy to remember. The electrons were so light, 0.0273 was it, we figured out, as far as mass, versus the nucleus of a helium atom moving. It's like a 18-wheel truck driving through tissue paper. So the effect of the electron cloud on the movement of the alpha particles was zero. There was no deflection or attraction or anything. So he proposed the structure moved right through the atom. Now, there are some great renditions online that show all kinds of pictures and stuff. I'm just going to draw one that is kind of a generalization that you could see. Now, this is a gold foil. And what his intention was to hammer it, mount it down to one atom. That's what he was trying to do, but of course couldn't do that. And so most pictures that they don't look like that. Most pictures will draw a bunch of atoms kind of lined up as such. usually 3 or 4 atoms, and then of course you got the nucleus is in the middle. And then what they show is this. About 99% plus straight through. Then they have a diagram that shows a slight obtuse deflection, less than 1% deflected. And then they show an example of a deflection, and they say less than 0.1% deflected, or no, bounces back. You
Reflected.
bounces back toward the source. So with that, the general scientific community accepted the fact that, well, the atom is mostly space consisting of the 2 parts, nucleus, and they took the numbers that I gave you earlier and constructed the generalizations. And that's all I need to say about the Rutherford model. So why don't y'all take a 10-minute break, and we need more. Let's start with the Bohr model. Now, the Bohr model was based upon analysis of bright line spectra. So that's the first thing you need to note. And what they did, as I've shown you earlier, is that they sent an electric charge through a discharge tube, is what those are technically called if you want to look them up in a supply catalog, filled with hydrogen gas. So let's just draw a simple discharge tube like this. It's what we were working with. And this was, of course, attached to a transformer or a very powerful battery. And what was generally observed was I got a purple and red, but I'm just going to say this is called a lavender color, is what they had in here. If and when it was observed through a diffraction grating, that's a little sheet of glass with about 30,000 lines per inch, scratched horizontally, parallel, whatever. Anyway, the beam of light goes in lavender, if you would. Goes here, but breaks out into, well, you can't see the UV one on the top end, but the other one is we can use. You have 1, 2, 3, and 4 lines generated out of this. You have a red line, as I showed you earlier, a green line, a blue one. I'm going to do my blue line. Here it is. Blue line, and where's my purple line? Here it is. Right here. So the lines represent, of course, discrete wavelengths, as I mentioned earlier, but there's a couple of things we need to look at in terms of light technology in order to analyze this. So the the board team was faced with evaluating what they were looking at. This is the raw data. Now, the red line is 656 nanometers. So you need to... Now, I'm not going to ask you to memorize line wavelengths. I'll put them on the test or whatever for you. That, give you all that data. I'd look it up too. Okay, and then there was 486 nanometers for the green one. And the blue one was 434. And the violet one, what was that? 410. Good enough. 410 nanometers. Now, back to the point of light. So this is electromagnetic radiation. So we're going to study the atom in terms of electromagnetic radiation. So what do you need from electromagnetic radiation? And you'll see me abbreviate EMR. And in general, is nothing but light. Okay? About light and what you'll need for at this level, your level, my level, anybody's level, and if you're going to go through this, is the following. Light travels through a vacuum at a constant speed. Or the speed of light in vacuum equals 3 times 10 to the 8th meters per second. That will be on your reference sheet at the back of the exam if you happen to need it. You will need it, I assure you. Light is electromagnetic radiation, which means that light travels in the form of waves. And the textbook says light is propagated in terms of waves. Is generally referred to as wave motion. In evaluating wave motion, you have certain variables. You have speed, frequency, wavelength, and energy. The terms in themselves are probably familiar to you, but I'm going to define them in terms of what you will need to invest in a working problem. Speed is only going to be one speed, and that's the speed of light. Speed of light is defined, is represented by the symbol lowercase c, and is equal to 3 times 10 to the 8th meters per second in vacuum, as I mentioned earlier. That's all I need to know about that. Frequency is the vibration rate of light wave, and that's in cycles per second. or CPS. The units that are typically attached to a frequency are seconds to the -1. And they don't, it's a 3 times 10 to the 14th seconds to the -1. Well, the 3 times 10 to the number 14 is the number of vibrations. So they don't put vibrations per second. They just leave it blank. I say they as in general context print. You look up frequency of something, it's going to come out as a -1, seconds to the -1 or /seconds. Or they'll just put CPS out there. Something of that nature. So just explaining what you were going to see and what it means. Wavelength, of course, is in a linear context. In publications on wavelengths of light, you'll find it in various dimensions. The most common is nanometers, okay, which is equal to 10 to the -9th of a meter. You will find it also in angstroms, which is 10 to the -8th of a meter. And angstroms usually has a capital A with a little O on top of it, and is 10 to the -8th of a meter. But nanometers is the most widely used. Now, you will have to make conversions from nanometers to meters to apply to certain equations. So let's say you're given, now this goes with right down here, simple conversion. How many meters equals, say, 2 times 10 to the, I don't know, let's not do that. 256 nanometers. That's what we need. I'm sorry. So convert 256 nanometers to meters. Okay? And so, for your benefit, let me just put one down here. Nanometers to meters. All right, that's 10 to the -9th of a meter is 1 nanometer. Little bitty. Okay? And then cross that out like that, and you have it in meters. 256 times 10 to the -9th meters. Okay, here's what I'm getting to. Putting that in standard form moves the decimal place 2 places to the left, and you'll wind up with 2.56 times 10 to the -7 meter. Now, why is that important? Because we're going to be talking about a very small field of interest right here. See this? We're going to be working with the red line, the green, blue, and violet lines. And in order to work problems with those numbers, you have to convert them to meters. So in essence, this is 6.56 times 10 to the -7th of a meter. You don't need, you won't see anything else in any other capacity. That's the only ones you'll have to deal with. Here, what's this in meters? Well, it's 4.86 times 10 to the -7. Same way here, 4.34 times 10 to the -7, and you'll see how this evolves as we go, because the data is going to come to you and says a wavelength of 656 nanometers has an energy of what? And this kind of thing. Well, when you do calculation, you've got to convert nanometers to meters. And so here's your example down here, is what I'm going to. Energy is what we call photon energy. Different people visualize the concept of wave motion and photon motion differently. Wave motion, like waves in an ocean. But photon motion, in my mind, is like raindrops going along. Now, they're not down like gravity pulls drops down to the earth. They go in all directions. But I look at, say, a photon of red light has a certain energy. It's like an energy packet. Well, it also has wavelengths. But if you're going to talk about an energy packet of red light, like the red line, it's discussed in terms of photons. So while it's discussed as a particle kind of characteristic, it's also discussed as a wave characteristic. That is the foundation for the next topic, quantum mechanics. It is based upon the wave-particle duality of light and the wave-particle duality of the electron. And so to describe light in terms of both particles and wave motion, it's very logical to establish some kind of particle light, and we call it simply a photon. There are blue photons, there are green photons, there are red ones, there are pink ones, and all colored photons. Okay, we're only interested in those 4 colors that are listed over here. And if you, I'll say I might give you a UV wavelength and say what's the energy or something like that. But it's very easy to deal with. And it's usually delta E is the symbology that we will use for that. Okay. With this, we then have certain formulas that we use to describe each one of these variables. Calculate the frequency of this wavelength, or calculate the wavelength given a frequency, or calculate the energy given wavelengths or frequencies and stuff of that nature. So you need to learn some generalization in terms of formulas now. They're very straightforward, but they are classic formulas that you need to learn in order to get through problems on the quizzes and exams. Okay. The first one is the relationship between frequency and wavelength. Okay, if we talk about wavelength, we're talking about something like this. This is a wave, two-dimensional wave, and it's represented by lambda. And that wave oscillates from here through a central axis or something like that. The time per oscillation is referred to as frequency. Now, in the colors of the rainbow, I'll let y'all get that down real quick. Share with you, and this you already know. What do you know about the order of the colors in the rainbow? Roy G. Biv, right? Okay, so colors. Red, orange, yellow, green, blue, indigo, and violet. And we want to describe the general wave variables of this acronym in terms of wavelength, general, frequency, and I'm going to go ahead and throw in energy while we're here. Why don't I throw in speed? It's always constant. It's the same number all the time. So you don't have to worry with that one. But if you were working with waves, wave motion in a generic sense, like air waves and sound waves and stuff like that, you'd have to calculate a velocity. You have to include that as a variable in that study. But in study of electromagnetic radiation, we luck out. We have one number, 3 times 10 to the 8 meters per second. Okay? All right. What can we say about the wavelengths as we move from red to violet? You have long wavelengths on the red end, and you have short wavelengths on the violet end. So as the color changes from red to violet, blue, and so forth, and go into the UV end, you have a compression of wavelengths. The wavelengths of red light and radio are on the radio wave end, and compressions on the violet end are on the very short radiation type, high energy radiation, short wavelengths. So you might want to draw a representation. There you go. So you got long wavelengths, very short wavelengths on that end. So let's move this down a little bit. All right, there's our wavelength relationship, frequency. Now these are vibrations per second, or cycles per second, right? So how fast is it moving? Well, if we have long wavelengths, you're going to have a low energy kind of thing. So we can generally say this is a low frequency. Low and slow is what I usually tell students. Slow vibrations. Low and slow. On the other end, you get up into real fast vibrations. very, very high speed vibrations in there. So as we go from long wavelengths to short wavelengths, we also go from low vibration rates to high vibration rates. And the last one is energy. Is that up here? Is parallel with frequency. So if you have a low vibration rates, you also have low energy. So we also have low energy. And as you move across to the violet end, you have high energy rates in here. Look at the way I've set it up for you. From the R to the V, Roy G. Biv, you have all the L's on the red end. So R are all the L's over here. Long, low frequencies, slow and slow, and low frequencies. Well, you only have one other option, is the opposite of whatever those are. And this goes short, this goes fast, and it goes high as you progress through the list. So as we work with the bright line spectra of the atom of hydrogen, we're going to start with the red end, low energies and long wavelengths, and this kind of thing, and low vibrations, and working up to the violet end, which are high energy and high vibration rates, high frequencies, and short wavelengths. So that's what we're going to do. Okay, now we want to look at the relationship between frequency and wavelength. So frequency versus wavelength. Okay, now what did we say up here about frequency and wavelength? Here's a wavelength and frequency. So we got long wavelengths but low frequencies, or we have short wavelengths but fast vibrations. That translates into an inverse relationship. Okay? So as the wavelengths get short, what happens to the frequency? It goes way up. So you decrease wavelength, increase frequency. So decrease wavelength, increase frequency. Everybody okay on that? How do we represent that in mathematical relationships as an inverse? So we have lambda, which is the symbology for our wavelength, is proportional to 1 over frequency. The textbook Ebbing uses a symbol. It's a Greek symbol, looks like that. I don't remember what it is, nu or something like that. And that confuses students. So I will be using F for frequency as we go through this. I will not be using the little symbol like this. But if you are doing independent reading in the Ebbing text, especially, when they talk about frequency, they're going to use this little symbol right here. Okay? So know that they're equal. F and this little new thing right here, drum kind of Greek thing. Okay. In order to connect these two, we put a proportionality constant. Well, it turns out the proportionality constant for the relationship between frequency and wavelength is the speed of light. It's a constant. Okay, so we could have lambda is equal to c 1 over frequency. Clean that up. Like that. And this then, c is equal to frequency times wavelength. So this is the first equation that you need to memorize, be aware of, to use. But you'll be given a wavelength, you have to calculate a frequency, or given a frequency and have to calculate a wavelength. We'll do that right now. What's the wavelength and frequency relationship in the red light? Well, we know the red light's 656 nanometers, okay? So calculate frequency red band of hydrogen spectrum. Wavelength is simply 656 nanometers. I showed you earlier that nanometers needs to be presented in meters because the speed of light is in meters per second. Now, I guess you can convert meters per second into nanometers per second, but that's not commonly done, and I don't expect you to do it on the exams either. So what did I do? I moved over 2 places, times 10 to the minus 7, and we're in meters. So that's 6.56 times 10 to the minus 7th of a meter. You'll do that all the time because we're not interested in something way out long, or in radio waves, and we're not interested in cosmic rays. So everything we're going to be playing with is going to be in this little visible band, visible light. So when I give you a wave, I might give you one that's in the UV, but it's still translated in the same way. If I give you 256 nanometers, it's 2.56 times 10 to the minus 7th meters. So whatever. You know, it's not going to be something radical. Okay, calculate the frequency of the band, and you're given a wavelength here. Well, based on this, C equals frequency times wavelength, and so it's asking us calculate frequency, which is speed of light over wavelength. And the speed of light, now sometimes I won't put that speed of light in the problem itself, and sometimes I do. But since it's always the same, is you either memorize it or go look on the reference sheet. It'll be there. 3 times 10 to the 8th meters per second divided by wavelength of 6.56 times 10 to the minus 7 meters. See how it comes out? When meters cancels out, all we have is those little slash seconds when it's finished. There. And 4.57 times 10 to the 14th slash seconds means cycles per second. And you might find it as a 4.57 times 10 to the 14th seconds to the minus 1, or CPS on the end of it. Okay? Now you might be given a frequency and asked to calculate a wavelength. So it's the same issue, except you use the appropriate substitution. Okay, that was the first one we want to look at. The second one is the energy relationship between frequency and energies. Okay, now we need to look at the relationship between energy and frequency. Earlier in the Roy G. Biv, I'm going to keep doing that, R-O-Y-G-B-I-V. Okay, we have low frequency, high frequency, okay, as we go across, and then we've got low energy, and we also have high energy. So from Roy to the R to the V, we have a direct relationship in this particular issue. So the change in energy, okay, is directly proportional to frequency. Now, unfortunately, the connecting proportionality constant is not the speed of light. It is called Planck's constant, and it's given in a symbol H, where H is I'm sure that's not spelled right. You can look it up, but I always spell it Planck's constant, okay? Planck's constant. And it will be attached to your reference sheet, and it is 6.63 times 10 to the minus 34 joule seconds, like that. That's your HF. That's what I was trying to write. 6.63 times 10 to the minus 34 joule seconds times frequency. So you'll always have that little constant in there. So given frequency, you can calculate the energy in terms of joules. So calculate delta E red given the
frequency we just calculated of 4.57 times 10 to the 14th reciprocal seconds, like that. And of course you'll use Planck's constant in this one, so delta E of the red line is equal to h times frequency. Okay, so that is 6.63 times 10 to the minus 34 joule seconds times a frequency of 4.57 times 10 to the 14 seconds to the minus 1. So seconds will drop out easy enough, and all you're left with is joules, and multiply the two together, and you'll have the energy of one photon of red light. That's what the equation is describing. I'll write it down in a minute. .02 times 10 to the minus 19th of a joule. That ain't much. That's one photon. What is the energy of 1 mole of photons? How would you do that? Well, if you got that number, you multiply it by Avogadro's number, right? Everybody okay on that? Okay. So energy, 1 mole red photons is equal to 6.02 times 10 to the 23rd, whatever units, that's always a mole, times 3.02 times 10 to the minus 19th, make that minus 19 of a joule. See what that looks like. Okay, that's 1.82 times 10 to the 5th joules. Light has a lot more energy than you think it has. And so 10 to the 5th joules, that's quite a bit. That's 182,000 joules divided by 1,000, say. And you have 182, yeah, okay, kilojoules. Okay, so that's your molar energy, and believe me, that's quite high. It'll burn a hole in the wall real fast. How do I know that? I've seen lasers do it. Red lasers will burn anything. Okay, and you can adjust them. They are quite powerful. So there's the energy of your red laser real quick. Okay. The second equation you need to keep in mind, but we're going to combine this equation with the C equals F lambda equation to find the relationship between energy and wavelength. Photon. Again, we go back to the Roy G. Biv and draw our conclusions about how the trends change from the red end to the violet end. So R, O, Y, G, B, I, V. Okay, so we're looking at wavelengths. Okay, what do we find in terms of wavelengths on the red end? Long wavelengths. Lambdas. And the relationship here is low energy. Now, then on this end we have short wavelengths and high energies. So as we go from the long to short versus the low to high energy factors, then we find it's an inverse relationship between energy and wavelengths. And so energy is proportional to 1 over wavelengths, which simply means as the wave increases, you're increasing lambda. This is decreasing your energy factor of the wave. And so we set it up as an inverse relationship. Now, the relationship 1 over here is still the Planck's relationship. Okay? Let's see. The equations we have are delta E equals H times frequency and C equals F lambda. Now, we can connect these two simultaneously through frequency right here. And so I can take this, solve for frequency to get C over lambda right there. And so I could put this back into that, and we have delta E equals H C over lambda, like that, which is the third equation you need to be aware of. So we'll come down here, and 1, 2, 1, 2. So your third equation is delta E equals HC over the wavelength, like that. Now C, of course, is a constant. H is a constant. And so that leaves us only with the wavelength value, and you must convert that to meters. All right? We'll get the same number, but let's go different color, I guess. Let's go with blue light, 434 nanometers. Let's say you're given lambda equals 434 nanometers. Blue light right here. Calculate energy using HC over lambda. Okay, all these three are very classic type calculations, and I've got several worksheets online, and if you just work through those and learn those formulas, that's all you'll see on test day, is these kind of things. Now I have another set of relationships that I have to develop independent of these, but as far as the basic wave variable type equations, this is it. Nothing radical here. Okay, so we want to use this. So what is H is 6.63 times 10 to the minus 34 joule seconds. That's given. C is given also. Is 3 times 10 to the 8th meters per second. And the lambda is 434 nanometers. Well, you can go calculate the other stuff in terms of nanometers, but right now it's easier to go with meters on the wavelength. So with 4.34 times 10 to the minus 7th of a meter. Everybody follow me on this one? I showed you earlier. It's given in nanometers. Just move the decimal 2 places to the left, 10 to the minus 7 meters. So these three will substitute very neatly. Move it up for you. And delta E equals HC over lambda, 6.63 times 10 to the minus 34 joule seconds, times 3 times 10 to the 8th meters per second, divided by, see if I can draw a straight line here, okay. Lambda is 4.34 times 10 to the minus 7 mole meter. And 4.58 times 10 to the minus 19th of a joule. That's 1 photon of green light. And multiply it by Avogadro's number if I happen to ask you the mole of photons. This kind of thing. So now your responsibility in wave calculations will center primarily on the bright line spectra of hydrogen. That's the first thing you need to understand. And to analyze those colors in terms of the wave variables, you want to use the C equals F lambda equation. You want to use delta E equals H times frequency equation, which is also HC over lambda equation. Actually, two of them right there. And the values that you have to deal with, you have constants in H, constants in C, and you'll have to work with the variables primarily in frequency, wavelength, and energy. Everybody get on that? Very, very straightforward. There's no surprise. There will be no surprises here. Okay? Now, the purpose of the comments just given are, these are the classic equations used for evaluating light from a wave variable standpoint. However, Bohr in his group had the problem of proving their postulates and their hypothesis in terms of concentric ring models. So, we're going to look at how they use the math and so forth to prove they match these types of variables. Spectrum. Hypothesis. Based upon the bright line spectrum, the electron cloud exists in concentric rings occupied by electrons at discrete distances from the nucleus. So based upon the bright line spectrum of the hydrogen atom, the electron cloud of the atom consists of concentric energy levels. I'm going to put out there my interpretation of energy levels. Rings, okay, occupied by electrons at discrete distances from the nucleus. So they are saying that here is the hydrogen nucleus, which is a proton, and we have a ring going around it. Now, that's a ring, that's only a fragment of the ring, of course, and we're going to call that ring N equal 1, first energy level. Then we're going to have a second energy level, is going to be here, N equal 2. And then we're going to have N equal 3. Notice how it's starting to get closer. It's logarithmic in the calculations, in mathematical calculations, and it begins to compress down as you approach out to 7. And it gets, I'll try to do the best I can, N equal 4. And then this one compresses even more, N equal 5. This one compresses even more, N equals 6, and this one gets way tight right here, N equal 7. And I'm going to stop at 7 because that's all we know in reality. There's 7 rows on the periodic chart. Each row represents a ring and the valence level is whatever the element rho is. Okay. Now, we put electrons in here, and as I mentioned earlier, the electron is not static in terms of being in the n=1. When subjected to energy, light energy comes in, the electron will absorb it, and then it bounces out and comes back. If it takes enough energy in, it will literally leave the element, and that's called ionization. Okay? So, when Bohr, everybody get everything they need here? Okay. So, Bohr reconstructed this and used a vertical display and showed how each level the electron transitions, and there were several. I'll show you. Okay, we're going to start here. Give yourself a little room. And here's the n=1. That's the first ring. And then I'm going to come up here and do n=2. And then we'll run n=3 here. And then we'll go 4. And then we'll come a little tighter. 5. n=6. And n=7. And nucleus is down there somewhere on the floor. When the electron absorbs energy, it can go anywhere in that atom. It can go, say if it's in 1, it can go to 2, it can go 3, 4, 5, 6, or 7. Okay, we do not see that. What we're interested in at this moment, there are absorption spectra, but we're looking at emission spectra. That's when we see the lines and things. That's an emission spectrum. What are the probable transitions is our interest here? Well, you can transition from wherever it went to back to 1, or you can transition from wherever it goes to back to 2, or you can transition from wherever it goes back to 3, or up, down to 4, and so forth. We're going to focus on all transitions that end on n=2. Why? Because that's where the visible range is. Ending on n=2 is the visible. If it ends on the n=1, it's ultraviolet, UV transitions. You don't see those. Those are invisible. If it ends on n=3, as they fall back down, it's the infrared, IR spectrum. Now, they have instruments. I say they, the scientific community has instruments that can detect those transitions and read them, specific transitions. And they are available if you want to go look them up. For our purposes, it's good enough to end on n=2 so that we can relate to the red, green, blue, and violet lines of the hydrogen spectrum. So in order to talk about, we're going to talk about anything that ends on 2. The electron probability of going to 7 means that it's going to fall back down to n=2, like that. When it does, it gives off energy. Or, case 2, the electron goes out to number 6 and falls down to 2. And here's a 5 to 2 transition, and a 4 to 2 transition, and a 3 to 2 transition. Well, it turns out that the 3 to 2 transition is a red line. The 4 to 2 transition is a green line. You probably can't see that, but that's a green line right there, believe it or not. Blue transition would be this next one. They're giving off those colors, those color lights. And violet would be the next one. And we cannot see 7 to 2. It's over in the UV range. So we're going to focus our attention primarily on these and these alone right here. Now, what constitutes a proof that this is true? when talking about the transitions of the atom and stuff like that. If we can develop mathematical equations that predict these transitions, both energy-wise and wave-wise, energy and wavelength-wise, that match the empirical relationships of wave motion, then we can connect the two and say, this is what's happening. Okay? Connect, what this means, and this is very important that you understand this in the context of the theory we're presenting. What proves this theory correct is that certain equations were derived from data of the bright line spectrum that proves there exists those transitions. The electron lives in 2 or lives in 1 or lives in 3 and goes to 2, but nothing in the middle. Okay? So what we're doing is connecting empirical relationships with theoretical, i.e. math relationships. Okay? That proves it. It's indisputable. I'm going to derive an equation that says when an electron lives in n equal 2, it has this much energy. And that same equation will predict that if the electron is in n equal 3, it's going to have so much extra energy. Okay? So what we're going to do is the equations of positional energy. That is the potential energy. Of the electron in a specific energy level. I may have to redraw this thing again, but you'll understand what I'm saying. The equation potential energy that we're talking about says that, well, here's the electron and it's living in n equal 5. How much energy does it have? Okay? It's not a transitional energy yet. It's a positional energy. It's like putting a marker pen on the table. Relative to the floor, it has some energy. And if I remove the table, it'd fall to the lower energy. And that's what I'm talking about here. A potential energy content of the electron while it's living in that ring. Okay? The equation we call En, which means the specific energy level you want to talk about. Now, the electron gives up energy as it moves down. So this is going to be an exothermic process. That's why I'm going to use negative. Negative A over N squared. That is it. A is a constant, proportionality constant, that was derived by experimental analysis. And you will also do it too. That's your lab. I'll show you how that came out. And so A, that shouldn't be on if then. And A is equal to 2.18. It's on your sheet when you need it for test. 10 to the minus 18th joules. That's called a energy constant. You'll find out later it'll be called the Rydberg energy. And there's also a Rydberg wave constant that I'll show you how to derive. We'll do it next class. Before we go into the, I can show you today. Give you it's really simple. I don't break something. Okay, let's talk n equal 3 to 2 transitions. Okay, what is the energy content of the electron when it's in number 3? Okay, we use this equation. So energy of the electron, n equal 3, is equal to minus A over n equal 3 squared, which is a minus 2.18 times 10 to the minus 18th of a joule. Okay? That's a given. A is given. N is 3 squared. It all comes out in joules, okay? 2.18 times 10 minus 1/8 divided by 9 is equal to 2.42 times 10 to the minus 19. Okay, so while the electron is sitting on that shelf, it has 2.42 times 10 to the minus 19th of a joule built up in it. Okay, how about number 2? Do the same thing for number 2. So En equal 2 is calculated in the same way. A over n squared is the derived equation that predicts the potential energy of the electron at a given level. Oh, you need to learn that, but that's an easy one. Same thing. A is 2.18 times 10 to the minus 18th of a joule over 2 squared. All right. So we'll try. I get 5.45 times 10 to the minus 19th of a joule. N equals 2. That's the energy content while it's in. Actually, I should be putting negatives in front of these. So there. What's the change in energy from 3 to 2? Energy in number 2 minus energy in number 3, maybe? Okay. Where am I going with this? I'm going to calculate using the first equations, the delta E equations, in terms of wavelengths that we're observing, like the red line. If it matches the energy of this differential, voila, I've proven my point, according to the science. Anyway, delta E equals En equal 2 minus E content of N equal 3. So N equal 2 is a minus 5.45 times 10 to the minus 19th of a joule. Minus 2.42 times 10 to the minus 19th of a joule also. So I'm going to take the difference in these two. Okay, 5.45 times 10 to the minus 19 minus 2.42 times 10 to the minus 19 is equal to 3.03 times 10 to the minus 19. Okay, so 3.03 times 10 to the minus 19 joule of energy released on N equal 3 to N equal 2 transition. Theoretical. So we have taken a mathematical expression here which defines the potential energy of the electron in a given orbital or ring, calculated its energy in each of the two rings and took the difference, which means the electron's moving from 3 to 2, and that's how much energy it gives off. Now, if this matches the same energy that we can calculate from the measurement of red light, delta E equals hc over lambda, and lambda is equal to 656 nanometers, or 6.56 10 to the minus 7th meter, then the red light is a result of the transition of the electron from N equal 3 to N equal 2. That's how they came up with this. Okay, so This is equal to 6.63 times 10 to the minus 34 joule seconds, and 3 times 10 to the 8th, I can't make 8, meters per second, divided by wavelength of 6.56 times 10 to the minus 7th of a meter. So let's see if we get this number. Now this will come out positive because it's an empirical formula that just defines a numerical value. The negative on this implies that the electron is moving from a higher energy level to a lower energy level, as in exothermic. Okay. Okay, so we got 6.63 times 10 to the minus 34 times 3 times 10 to the 8th equals, and then divide that by 6.56 times 10 to the minus 7. Woo! We get 3.03 times 10 to the minus 19th of a joule. QED, quote et demonstrandum. So we set out to prove by empirical theory a calculated value of the transition energy matches the calculated value from an empirical relationship that everybody uses. Everybody knew this right here. But that does not tell you that it has a transition. Using the A over N squared defines the potential energy, was derived to be the potential energy of the electron while in a given ring. We can track all the way up and down. You can calculate the transition energy from each level. Now the only thing left is the wavelength. So now we got to calculate wavelength that matches this. It's got to come out red. Okay? Now we'll use the empirical relationship delta E equals hc over lambda and calculate that. But we're going to calculate it in terms of empirical relationships. Here's what we're going to do. E sub n is equal to minus A over n squared for whatever ring you're in. Delta E is going to be E final minus E initial. Yeah? That's what 2 and 3, that's how we did that. Okay, E final, we're just going to say is minus A over n squared final, because that's the positional energy. That's the delta E. Okay, minus a minus A over n squared initial. Like that. And we'll make, I'll tell you what, let me put it in here. There we go. Just like that. And that's what we did earlier. I mean, we calculated the energy content of ring 1, 3 and ring 2, and we took a difference in them. But this is kind of in a mathematical layout. Okay, I rearrange. Minus times a minus is a plus. So I'll have A over n squared initial minus A over n squared final. Ta-da! And that equals a delta E. Right there. Which is equal to hc over lambda, yes? So that's why I say you can connect this transition. We already did that earlier, and we found out their match. 3.03 times 10 to the minus 19 using this equation matches the calculation we use for this equation right here. Now, mathematically, you rearrange. You factor out the alpha, the A, constant, A, and you wind up 1 over n squared initial minus 1 over n squared final is equal to hc over lambda. A is a constant, H is a constant, C is a constant. Transposition H and C to the left side. A over HC is what we'll wind up with. So now we have A over HC, 1 over n squared initial minus 1 over n squared final, and an equation in terms of the wavelength. Lambda, like that. Well, it turns out when you put 2.18 times 10 to the minus 34, okay, minus 18 for that one. And H is 6.63 times 10 to the minus 34. And C is 3 times 10 to the 8 meters per second. And rearrange it to centimeters, reciprocal centimeters. What you come out with is let me move this up. 1 over lambda is equal to R sub H. That's called the Rydberg wave constant. The A value up here is a Rydberg energy constant. See, this is lambda, and so you have 1 over n squared minus 1 over n squared, initial and final. And there's your mathematical derivation. So we'll use this equation to calculate the wavelength and see if it comes out red based upon predicting 3 to 2 transition. You don't see anything else in that equation other than the constant here. So the wavelength is simply in terms of the transition, and we want to match that with the wavelength that we're observing in the spectroscope. If that's true, then we have double proven the concentric ring concept. So 1 over lambda is equal to RH. Oh, I forgot to tell you what R is. RH is 106. 109,678 centimeters to the minus 1. It'll be given. That's what your value is for R. So that's 109,678 centimeters to the minus 1. 1 over, where did we start? Ring 3. Minus, where did we end? On 2. Now, the results will come out in reciprocal centimeters, so you have to revert, take the reciprocal after you finish. So 1 over lambda is equal to, I'll string it out for academic reasons, okay, that would come out. You need to change that to a positive. There's no negative wavelengths, so the equation itself always comes out positive. And I don't want to go through all the math that proves that, okay? You don't need it either. Just remember, waves are always positive. So when you're doing this wavelength calculation. And that's going to come out in centimeters to the minus 1. Okay? So now, let's take reciprocal of 9. 9 reciprocal is 0.111, so 109,678 onto 0.111 minus 0.25 centimeters to the minus 1. Right up a little bit. And so that's minus 0.25. That gives me a minus. I guess I could just go ahead and put a minus in here, and then when you take this differential, it'll all turn out positive. So that's the simplest thing I can think of real in the short term. So this minus this will give us minus 109,678 times a minus 0.139 centimeters minus 1. And so times 109,678, and that's equal to 15,233. That comes out plus, minus times a minus a plus. So 15,233 centimeters to the minus 1 over lambda. And so now lambda is equal to 15233 come on JP, 15,233 centimeters to the minus 1, and we're going to take the reciprocal of that. So I'm going to take the reciprocal, dink, second scientific. I got 6.56 times 10 to the minus 5. 6.56 times 10 to the minus 5 centimeters. That number matches the number for the red line energy wavelength transition, 656 nanometers. This honestly translates to 656 nanometers. You can go through the conversion. This is red line. So in two formats, we've identified the energy of the transition as 3.03 times 10 to the minus 19th. That matches empirical relationships. And then we calculated a wavelength using theoretical concepts, and that matches the observation of the red line. And this works the same way for any color. One more thing here. You can determine very simply the relationship constants, these constants. The Rydberg energy equation is equal to A 1 over n squared minus 1 over n squared initial final, like that. Well, this is of the form A y equals mx plus b, where it starts, minus n's final. So you have an energy number at m, x, and plus minus b, which is irrelevant. The b is irrelevant. What you're looking for is, what is this m value? So you can take the n values, like you're starting at 5, 4, 3, where you're transitioning. For n equal 5 to 2, 4 to 2, and 3 to 2. Okay? You have 1 over 5 squared, 1 over 4 squared, and 1 over 3 squared. And that's 1 over 25, and that's equal to 1 over 16, and that's equal to 1 over 9. Okay? So you have your x values. This represents x values. Well, you calculate the E values based on the wavelengths. Okay, the E values are hc over lambda for each one in quantities of 10 to the minus 19. That's what each one will come out. Something times 10 to the minus 19. For a 5 to 2 transition, you'd have to do the green line, I mean the violet line. And the next one would be the blue line. This would be the green line transition. Oh, no, that's a red, green, blue. I'm sorry. And plot, and I'm going to go through this with you next time anyway. Plot the values of delta E that you calculate for each transition, in transition, is equal to, let's see, now that's the Y value. Plot the X values, 1 over n squared initial versus delta E in whatever that energy change is. For this, it starts here and goes, say, 5 to 2 or something like that. That would be a 25, 1 over 25 versus whatever the energy trend. So I'd have, this is my X, these are my Y's. And so this one would be 1 over 5 squared, 1 over 4 squared, 1 over 3 squared, 3 to 2. And then I'd have delta E for the 5 to 2, that's the blue line. And this is delta E for the green line. And delta E for the red line. And so if you plot delta E versus 1 over n squared, you get a straight line like that. The slope in this case is equal to the Rydberg energy constant. You do the same thing for 1 over lambda equation, and you'll get the R value out of that. I'll bring you sheets on that next time, and it's just a time. If you can use Excel, you can do it in about 15 minutes. Thank you. That's all I've got for today. We'll start on the Schrodinger equation next. Okay.
We'll see you guys.
Y'all have